Hello, I'm Nick Poolos. I'm from the University of Washington in Seattle, Washington, and I have 3 minutes here to tell you about my favorite ion channel, the hyperpolarization activated cyclic nucleotide gated, or otherwise known as HCN channel, and why I think it's important in epilepsy, why I and many others think it's important in epilepsy. So the HCN channel is really a unique ion channel. If you wanted to talk about it structurally, it looks like a potassium channel, but in fact it has only partial permeability of potassium and actually lets in quite a bit of sodium. I think the key feature about this ion channel that really makes it unique as far as neurons are considered is that it is open at the typical resting potential of neurons. There are very few ion channels that are actually open at neuronal resting potential, and so that means that this channel gives a continuous sort of leakage current that can be modulated up or down by the neuron to affect its excitability. There are a couple of different subtypes that are particularly important in brain. HCN1 is the subtype that is most prevalent in cortex and hippocampus, and HCN2 is mostly in subcortical structures like the thalamus. Another key feature about this ion channel is that it is in cortical neurons predominantly localized to the apical dendrites of the neuron. In fact, here we see a picture of a typical hippocampal pyramidal neuron, and these neurons put about 10 times as many of these channels in the dendrites as they do in the cell body. Now, why do they go to all the trouble of doing that? Well, we think the reason is that the neuron wants these channels at the sites of excitatory synaptic input. And by modulating these channels, they can control the flow of excitation to the cell body. So what is the role of these channels in epilepsy? Well, the most straightforward data that we have is that genetic deletion of these channels, such as the HCN2 channels, which are mostly in thalamus, generate a generalized epilepsy like absence. Deletion of HCN1 channels do not seem to generate epilepsy by themselves, but if you produce a neural insult of some kind that would ordinarily produce epilepsy, the process by which epilepsy occurs, epileptogenesis, is accelerated 6 times. There are numerous examples in animal models where the current generated by HCN channels, which we call IH, is decreased after neural insults such as status epilepticus, hypoxia, and so forth. And also, IH appears to be upregulated by some anti-epileptic drugs like lamotrigine, and may be one of their key mechanisms of action. We have investigated how HCN channels are altered in epilepsy, and it appears that the time course of these events, which are summarized here in a somewhat complicated slide, demonstrate that HCN channels after a neural insult are downregulated very rapidly as an hour, and essentially persist permanently for the life of the experimental animal. This process seems to occur via a number of different mechanisms. Some are epigenetic, and some are post-translational, such as altered phosphorylation signaling. But I think the bottom line is that because these ion channels appear to have a powerful influence on cortical excitability and are altered in a variety of epilepsy models, we think that targeting these mechanisms via possibly novel anti-epileptic mechanisms or even genetic mechanisms may provide some future therapeutic possibilities. So in summary, that is why we're enthusiastic about these ion channels and their role in epilepsy, and thank you for your attention.